This is linear algebra, lecture 13. And we've been trying to understand linear transformations T on finite dimensional vector spaces. So dimension of V is, let's say, N. Dimension of W is M. And we have this linear transformation T. And if we fix the basis, or if we fix bases for V and W, we can represent T by a matrix. Say the basis for V is E1 up to En, and the basis for W is F1 up to Fn. Or maybe for simplicity, let me just call this basis with the E vectors script E, and the basis with the F vectors script F. So if V has coordinates x1 to xn with respect to the basis E, then T of V its coordinates with respect to the basis F will be, I write T V sub E. So T is an m by n matrix. It's called A sometimes for short. It's an m by n matrix where it's defined in the usual way that if A is A11 up to A1n, this is A M1 up to A Mn. We take T of the basis vector Ej, its coordinates with respect to the basis F, or say this. T of Aj is some linear combination of the basis vectors in W. So those are the F sub I. So it's Aij F sub I. I goes from 1 up to M. So A1j down to AMJ, this column vector is the coordinate vector for T of Ej with respect to the basis F. I'm not sure I'm saying this is simple, making this as simple as it is, but it's something that we've seen over and over again. This is the way you associate a matrix to a linear transformation. Let me just repeat this just to make it a little bit clearer. So we have V generated by n vectors, E1 up to En, W generated by m vectors, W1 up to F sub 1 up to F sub m, and T from V to W, a linear transformation, is completely determined by how it acts on the basis vectors. So let's say that T of the vector Ej, that's something in W, so it's a linear combination of the vectors in W. This is summation Aij W F sub I. I goes from 1 up to M. And we define the m by n matrix A equal Aij with these as its coordinates. And this has the property that if we take V to be summation xj ej, j goes from 1 up to n. So this is writing a vector in V as a linear combination of the e's. So the coordinate vector for V with respect to the basis E is the n-tuple x1 down to x of n in Rn. That's the coordinate vector for V with respect to E. And if we take T of V, that's a vector in W, and we write its coordinate vector with respect to the basis F, this is going to be exactly A, the matrix A applied to the coordinate vector for V. So if we let this be y1 up to y sub m, this is A, x1 down to x of n. It's n by n matrix. So, I mean, this is the standard way we associate a matrix to a linear transformation. And we would like, this is sort of a goal, to find bases for V and W so that the matrix A is as simple as possible. So that's kind of a goal. Because a simple matrix for A means we have a simple way of understanding the linear transformation T. So there's one method, there's one idea that we've discussed before, and it's in fact part of the fundamental theorem, one of the fundamental theorems in linear algebra, that says the following. So I'll repeat it because it can't be repeated too often. We have T, a linear transformation from V to W. Dimension of V is n. Dimension of W is R. And associated to this linear transformation, we have the kernel of T, which is all the vectors V in V, such that T of V is 0. This is a subspace of V. And we have the image of T, which is all the vectors W in W, such that W is T of V for some element, some vector in the vector space V. So our standard picture is the following. Here's V, here's W, here's the linear transformation from V to W. We have the 0 vector in V, we have the 0 vector in W, and we know that 0 gets mapped to 0, but in general, there's a whole subspace of elements that get mapped to 0. That's the kernel of T. And over in W, we have the image of T. So any vector V gets sent to something T of V in the image of W, in the image of T contained in W. And what is called the rank of T is the dimension of the image of T. So the image of T is a subspace of W. Every subspace has a dimension. And the basic theorem says that the dimension of V is the dimension of the kernel of T plus the dimension of the image of T. The dimension of the kernel of T is sometimes called the nullity of T, and the dimension of the image of T is the rank of T. Dimension of the kernel of T is what is called the nullity of T. Right? So that's the fundamental theorem. You have to know this theorem and you have to know how to prove it. And I'll show again how to prove it. So suppose we let K be the nullity of T, which is the dimension of the kernel of T. So let V sub 1, V2 up to Vk be a basis for, let me call this prime. Be a basis for the kernel. And we can extend, let n minus k be equal to r. So we can extend to a basis for all of v. That is, there exist, and this is a fundamental phrase, there exist vectors v1 up to vr such that the set of vectors v1 up to vr and v1 prime up to vk prime is a basis for all of v. So we have v is generated by the set of vectors v1 up to vr and v1 prime up to v sub k prime, where r plus k equals n. And v1 up to vk is a basis for the subspace kernel of T. I claim that T of v1 up to T of vr is a basis for the image of T. So how do we prove that? Suppose I take any vector v in the vector space V. So V is some linear combination, C sub I, V sub I goes from 1 up to R, plus summation C sub I prime, V sub I prime, I goes from 1 up to K. These are the n vectors in the basis. So T of V is T of this vector, that's summation C sub I, T of VI, I goes from 1 up to R, plus summation C sub I, T of V sub I, T of C sub I prime, T of V sub I prime, I goes from 1 up to K. But the VI primes are all in the kernel. So this is a linear combination of just zero vectors. This is the zero vector. So this is summation I goes from 1 up to R, C sub I, T of V sub I. Which means that every vector in the image of T is a linear combination of the R vectors T of V1 up to T of V sub R. Let me show that these not only generate the image, but they're a basis for the image. That is, they're linearly independent. So suppose summation C sub I, T of V sub I goes from 1 up to R, is the zero vector in W. So the zero vector is this, which is summation C sub I, V of I goes from 1 up to R, T of that, which means summation C sub I, V sub I goes from 1 up to R, is in the kernel of T, which means summation C sub I, V sub I goes from 1 up to R, is some linear combination of the basis for the kernel, which are the vectors I going from 1 up to k, v sub I prime. But the VI's and the VI primes are linearly independent. So CI and CI prime are 0 for all I. So what we have then is that we have V is generated by V1 up to VR, V1 prime up to VK prime, R plus K equals N, and T of V1, T of V2 up to T of VK are a basis for the image of T. So over here we have the vector space W. Sitting inside of it is the image of T, and we have these vectors T of VI. So let W sub I equal T of VI for I going from 1 to R. These are linearly independent. These are linearly independent in W. And we can extend any linearly independent set to a basis W1 up to WR, WR plus 1 up to WM. That's some basis for W. And T of VI is equal to WI for I going from 1 up to R. And T of VI prime is 0 for I going from 1 up to K. So the matrix for T with respect to these two bases is the m by n matrix, which looks like this. T of V1 is W1. T of V2 is W2 up to T of VR. This is the rth row. They're ones down the diagonal. So this is like the R by R submatrix. This is just ones down the diagonals, like the identity submatrix, and everything else is 0. So what this tells us is whenever you have a linear transformation T from V to W, there always exists a basis for V and the basis for W, such that the matrix for T with respect to this basis is, it's an m by n matrix. The rank R is no bigger, it's less than the smaller of m and n. So you have this R by R identity matrix in the upper left-hand corner of the matrix for the linear transformation T, and everything else is 0. So there's nothing simpler than this. This is simplest. I mean, of all possible m by n matrices that describe a linear transformation of rank R, the fact that you have bases, that there exist bases such that the matrix has this form, is the simplest possible description of your linear transformation. The problem is no way to compute it. There's no effective way that we know, computationally effective. We know that bases exist so that the matrix with respect to those bases has this form, but we don't know how to compute the basis. So we would like to remedy that. This is as simple as it can possibly be, but you can't compute it. And then the question becomes, is there something almost as simple that you can't compute? Now, there's a special case, which is very important, where we have a linear operator, T. That just means a linear transformation from a vector space V to itself. V is finite dimensional. The dimension of V is equal to n. And the special case is the following theorem. If T is described or given by a symmetric matrix A. So there's a symmetric matrix. Symmetric means A equals A transpose. The transpose of a matrix is the matrix you obtain by interchanging the rows and columns. So if A is an n by n matrix, the transpose is also an n by n matrix. So if T is given by a symmetric matrix, then there exists an orthonormal basis of eigenvectors of V. So this basis, let's say the basis is E1, E2 up to E sub n. T of the vector EJ is some scalar times EJ. That's what it means to be an eigenvector. T of the vector is a scalar multiple of itself. And then the basis, then the matrix with respect to this new basis is diagonal. Lambda 1, lambda 2, down to lambda n, zeros everywhere else. So this is really very beautiful. If you have a symmetric linear transformation or a symmetric matrix, you can always find there exists a basis with respect to which the matrix is diagonal. The scalars down the diagonal are the eigenvalues of the matrix. And if you have, and then you understand this linear transformation completely. If V is a vector, which is some linear combination, Cj, Ej, J goes from 1 to n, is any vector in the vector space V, then T of V is T of summation Cj, Ej, and it goes from 1 up to n. This is summation Cj, T of Ej, J goes from 1 up to n, but T of Ej is just lambda J, Vj. So if you have a vector V and you apply the linear transformation to it, you simply multiply each coordinate of Ej. You multiply the coordinate of Ej by lambda J. That's very simple. That's exactly what it means to have a diagonal matrix. So when you have a symmetric matrix or a symmetric linear operator, you have this famous theorem that says every symmetric matrix can be diagonalized. That is, there is a basis for the vector space with respect to which the matrix is diagonal, and the basis is actually an orthonormal basis. So that's very good. However, not every matrix is symmetric. So this is a great theorem when you have a symmetric matrix, but it doesn't tell you anything when you don't have a symmetric matrix. And in particular, it doesn't tell you anything when you have a rectangular matrix that's not a square matrix. So the general problem is still given any, no symmetry condition or anything else, given any m by n matrix A, let's just say, or equivalently, given any linear transformation T from V to W, where the dimension of V is n, dimension of W is m, find bases for V and W with respect to which are such that the matrix for T is, what shall I say, simple. Put that in quotation marks, or easy to understand. That's the general problem. And one of the big results in linear algebra is that this is always possible. So this is the theorem. It's the theorem on what is called the singular value decomposition. Theorem called the singular value decomposition. So we have a linear transformation T from V to W. Dimension of V is n, dimension of W is m. And the theorem says the following. That R be the rank of T, which is the dimension of the subspace, the image of T in W. There exist orthonormal bases. That means in each orthonormal basis, every basis vector has length 1, and every pair of basis vectors are orthogonal or perpendicular. So there exist orthonormal bases V1 up to Vn for V, and W1 up to Wm for W, and there exist positive numbers, sigma 1, I write them in decreasing order, sigma 2, greater than or sigma r, greater than 0. So these are R strictly positive numbers written in decreasing order, such that T of Vi is sigma I Wi, for I going from 1 up to R, and T of V I is the 0 vector for I going from R plus 1 up to n. So the matrix for T with respect to these two bases will look like the following. You have an R by R submatrix. Down the diagonal, you have these singular values, sigma 1 up to sigma r. Above and below are zeros. So this is an R by R diagonal matrix, and everything else is 0. So this is M minus R, this is R, this is N minus R, because this is an M by N matrix. You have a matrix, it's a rectangular matrix, it's an M by N matrix, with these positive numbers sigma down the diagonal of the upper left-hand R by R submatrix, and everywhere else is 0. And the point of this is that this is something that we can often compute. Now, the proof of this is not extremely complicated, but it does take 3 or 4 hours to prove. And in the beginning linear algebra course, one often doesn't prove it. In any case, we don't have the time. But this is a theorem. And what I'm going to show is examples of how one actually computes this singular value decomposition. That is the point of all this. So a key observation is the following, right? So we know that N by N symmetric matrices have I should say every N by N symmetric matrix has an orthogonal basis of eigenvectors. That's our big theorem about symmetric matrices. The trouble is, if A is an M by N matrix, first of all, it's not a square matrix, and in no sense is it symmetric. However, if A is M by N, the transpose of A is the N by M matrix, A sub T, with coordinates Aij superscript T. And the definition of the transpose of a matrix is that the ijth coordinate of the transpose is the jith coordinate of the original matrix. That's the definition of the transpose. So we have this matrix A, Aij, M by N. The transpose AT is N by M. So if I take AT times A, this is an N by M matrix. This is an M by N matrix. So when I multiply them, the product is N by N. So let me just call this S for the moment. So given any M by N matrix, if I take the transpose of A times A, that gives me a square N by N matrix. And I claim that the N by N matrix, A transpose A, is symmetric. And the proof relies on the following two facts. First of all, if you have a product of two matrices, the transpose of the product is the product of the transposes in the opposite order. And if you take a matrix, take its transpose, and take the transpose of that, you get back to A, right? So it's like, for example, A23 becomes A32 becomes A23 again. The transpose of the matrix is the matrix. So now let's look at S transpose. So this is S. S transpose is A transpose A transpose. This is the transpose of a product. So it's the product of the factors in the opposite order. This is A transpose times A transpose transpose. But the transpose of A is A. So this is A transpose A, and A transpose A is S. So S transpose equals S. End of proof. S is symmetric. So the matrix A transpose A has A transpose A has a this is an n by n matrix. It has an orthogonal, sorry, not just orthogonal, an orthonormal basis of eigenvectors. V1 up to Vn. So A transpose A has an orthogonal basis of eigenvectors with eigenvalues lambda 1 up to lambda n. And I can rearrange the vectors so that these eigenvalues, sorry, that's an orthogonal basis of eigenvalues that are real. I'll just write real. They're real numbers, they're not complex numbers. So I can write them in decreasing order. Remember that R is the rank of A. And so actually, so I'm really stating this as a theorem, and these are non-negative. A transpose A has n real non-negative eigenvalues. And there's an orthonormal basis of eigenvectors. Then that W sub j, so remember A or T is goes from, let's just write it as everything's Rn to Rm. So A of each vector Vj is some, no, I should want to say this, but so define, this is an orthonormal basis in the vector space V, and each of these vectors is an eigenvector for A transpose A with eigenvalue lambda sub I. For each of these numbers, take the square root. So let sigma j be the square root of lambda j for j going from 1 up to n. So the sigmas are also decreasing. Sigma 1 greater than or equal to sigma 2, greater than or equal to sigma n, greater than or equal to 0. Suppose we define w sub j to be one over sigma j, a of vj, for j going from 1 up to r. So if, no. All right, so this is the theorem. Then W1 up to W sub R are linearly independent. And in fact, orthonormal. And extend to a basis for W, which is Rm. So the W's are a basis, the vectors W1 up to Wn give a basis for W, and the V's are a basis for V. And the claim is that, so AVJ is sigma j Wj for j going from 1 up to R, and A of Vj is 0 for j going from R plus 1 to n. And so you get the matrix for A with respect to this new basis. You have an R by R submatrix with sigma 1 down to sigma R on the main diagonal and everything else 0. So the point of this exercise is the singular value decomposition says you can find a basis for V and W with the desired properties. And this is an algorithm to find the bases. So you look at A transpose A. It's a symmetric matrix. It has an orthonormal basis of eigenvectors. That is the basis you pick for V. You use those vectors to construct a basis for W, and that gives you the singular value decomposition. So maybe the simplest thing, even though it's not so simple, is to work out some examples and see what happens. So let's start with an example. And the point is, this works for arbitrary rectangular matrices. We don't have to look at just 2 by 2 matrices. So we have, let's say we have the matrix 1, this is going to be a 4 by 3 matrix. 1, 2, 1, 2, minus 2, 1, minus 2, 1, 3, 1, minus 3, 1. So that's the matrix A. And the matrix A transpose, the first column becomes the first row. The second column becomes the second row. The third column becomes the third row. So this is 4 by 3. This is 3 by 4. If I take A transpose A, what do I get? So I have to do this matrix multiplication. 1, 2, 1, 2, minus 2, 1, minus 2, 1, 3, 1, minus 3, minus 1, times 1, 2, 1, 2, minus 2, 1, minus 2, 1, 3, 1, minus 3, minus 1. So row into column, I get 1 plus 4 plus 1 plus 4 is 10. I get minus 2 plus 2, minus 2 plus 2 is 0. 3 plus 2 is 5, minus 3 minus 2, 5 minus 5 is 0. Let's see, I know this is 0 because this is a symmetric matrix, so I already know this. What is the 2 by 2 entry? Second row into second column. 4 plus 1 plus 4 plus 1 is 10. Let's see what goes here. Second row, third column. Minus 6 plus 1 is minus 5. Plus 6 minus 1. Minus 5 plus 5 is 0. This makes this a 0. What's down here? 9 plus 1 is 10. Plus 9 plus 1 is 20. So this is the matrix A transpose A. And not only is it symmetric, but it's already in diagonal form. What are the eigenvalues? So you look at this matrix, the eigenvalues are 10, 10, and 20. Let me put them in decreasing order. So I want to find a basis, an orthonormal basis for this linear transformation from R3 to R3. So suppose I let the vector V1 be equal to E3, right? Then let me just call this S for the moment. So S of V1 is S of E3. S of E3 is 0, that's S of 0, 0, 1, which is 0, 0, 20, which is 20 times 0, 0, 1, which is 20 E3. 20 E3, which is 20 V1. So V1 is this unit vector with it's an eigenvector with eigenvalue 20. I can take V2 to be E1 and V3 to be E2. So S of V2 is S of E1. That's this first column, which is E1, which is S of E1 is this first column, 10, 0, 0. That's 10 times 1, 0, 0, which is 10 E1, which is 10 V2, and S of V3 is S of E2. S of E2 is 0, 10, 0, which is 10 times 0, 1, 0, which is 10 E2, which is 10 V3. I want to let W1 be 1 over the square root of 20 times A of V1. What is A of V1? Let me just write this out. 1 over the square root of 20. A is 1, 2, 1, 2, minus 2, 1, minus 2, 1, 3, 1, minus 3, minus 1. Apply to V1, which is E3, 0, 0, 1. So this is 1 over root 20, 3, 1, minus 3, minus 1. The length of this vector is the square root of 20. So this is a unit vector. W2 is 1 over the square root of 10. A of V2, that's 1 over root 10. A of E1, which is the first column, 1 over square root of 10, 1, 2, 1, 2. And W3 is 1 over root 10 A of V3, which is 1 over root 10 A of V2, which is 1 over root 10 times the second column, minus 2, 1, minus 2, 1. So I've constructed bases for R3 and R2, bases for R3 and R4, which is the singular value decomposition. So let me just summarize all this. I started out with a 3 by 4 matrix, 4 by 3 matrix. 1, 2, 1, 2, minus 2, 1, minus 2, 1, 3, 1, minus 3, minus 1. And I construct the basis for R3, where V1 is 0, 0, 1, V2 is 1, 0, 0, V3 is 0, 1, 0. This is a basis for R3. And I construct a basis for W, which is R4. Now, let's see. So the first vector, W1, is 1 over root 20, 3, 1, minus 3, minus 1. W2 is 1 over root 10, 1, 2, 1, 2. W3 is 1 over root 10 minus 2, 1, minus 2, 1. Now, this is a set of 3 vectors for R4. I need a 4th vector, because I need a vector which is linearly independent of these, orthogonal to these, and has a length 1. So I can take any vector. So to compute W4, take any vector which is not in the subspace generated by W1, W2, and W3. For example, E1. And then if I use the Gram-Schmidt orthonormalization process, I subtract off from E1 the component of E1 in the direction of each of these vectors. So I can subtract off E1 inner product with W1, W1, minus E1 inner product with W2, W2, minus E1 inner product W3 with the vector W3. And I'm going to call that W4. At least that's the first step. I'll call this W4 total. So what is this? E1 is the vector 1, 0, 0, 0. W1 is the vector 1 over root 20, 3, 1, minus 3, minus 1. And what is the inner product of E1 and W1? The inner product of these two vectors is 3 over root 20. So it's minus 3 over root 20 times this. Minus, what is the vector W2? W2 is 1 over root 10, 1, 2, 1, 2. What is the inner product of E1 with this? It is 1 over root 10. Minus scalar multiple of W3. W3 is 1 over root 10 minus 2, 1, minus 2, 1. And the inner product of this with E1 is minus 2 over root 10. So let's see if I can do this calculation correctly. I have 1, 0, 0, 0. Minus, this is 3 over 20. So this is minus 3 over 20. 3, 1, minus 3, minus 1. This is 1 over 10, minus 1 over 10, 1, 2, 1, 2. This is plus 2 over 10, or 1/5, minus 2, 1, minus 2, 1. So I have to compute all this. Let me put everything over a common denominator of 20. 1 over 10 is 2 over 20. 1 over 5 is 4 over 20. So what do I get? When I subtract these, compute this linear combination, I get 1 minus 9 over 20 minus 2 over 20. That's minus 5 over 20. Minus 10 over 20. Minus 2 over 20 is minus 12 over 20. Minus 8 is minus 20 over 20. That's minus 9 minus 2 is minus 9 minus 2 is minus 11. No, can't be right. 3 over 20 times 3, it's 9 over 20. And these are 1, 2 over 20, so that's 11, 8. E1 inner product of E1 and W1 with W1. W1 is the vector 1 over root 20, 3, 1, minus 3, minus 1. The inner product of this with E1 is 3 over root 20. So this gives me 3 over 20 times this. This is 1 over root 10, 1, 2, 1, 2. The inner product of this with E1 is 1 over root 10. So that's 1 over 10. Okay. 3 over 20 minus 1 over 10. Here I have the inner product of E1 and W3. W3 is minus 2, 1, minus 2, 1, 1 over root 10. And the inner product of that with E1 is minus 2 over root 10. So this gives me plus 4 over 10. So this is 3 over 20 So this is 1 over 20 times what vector? So this is minus 9 minus 2 is minus 11 minus 8 is minus 19. 20 minus 19 is 1. So this first coordinate is 1 over 20. Everything's fine. Second coordinate over 20, I'm subtracting minus 3 minus 4 is minus 7, plus 4, minus 7 plus 4 is minus 3. 0 minus 3 is minus 3. And the third coordinate is 0 minus, I have 9 over 20 minus 2 over 20 is 7 over 20. Minus 8 over 20 is minus 1 over 20. And the fourth coordinate is 0. 3 over 20 minus 4 is minus 1 over 20. Plus 4 over 20 is plus 3 over 20. So this vector is perpendicular to the first three vectors, but it's not a vector of unit length. It's the length of this W4 squared is 1 plus 9 plus 1 plus 9 is 20 over 20 squared is 1 over 20. 1 over 20. So I have to divide by the square root, 1 over the length. So 1 over 20 over 1 over the square root of 20 is 1 over the square root of 20. So my fourth vector, let me just squeeze it in here, W4 will be 1 over root 20 times 1 minus 3 minus 1, 3. So I've now constructed a basis for R4, a basis for R3. And with respect to these bases, my matrix A is going to look like, it has to be a 4 by 3 matrix. Down the diagonal, we have the sigmas, which are square root of 20, square root of 10, square root of 10, 0, 0, 0. So with respect to these bases, these orthonormal bases for V and W, this is what the matrix looks like. Let me just keep doing examples because I want this to be, if you like, on the record as part of our lectures, because this is something you should see in a linear algebra introductory course, but it's not going to be on the final exam. But it's worth just trying to understand a little. Let's take a simpler example. Let's take a 2 by 2 example. So let's take a 2 by 3 example. Suppose I take the matrix A, or suppose we have T, a linear transformation from R3 to R2. So this is given by a 2 by 3 matrix with respect to the standard basis. Let's say the 2 by 3 matrix A for my linear transformation is going to be 1, 0, 0, 1, 1, 0. So for this linear transformation, T of E1, which is T of 1, 0, 0, is 1, 0. T of E2 is T of 0, 1, 0, is 0, 1. And T of E3, which is T of 0, 0, 1, is also 1, 0. That's how this matrix operates. Let's compute A transpose A. So A transpose A, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. So this is going to be a 3 by 3 symmetric matrix. This matrix S, let's call it. What are the coordinates? I have 1, 0, 1, 0, 1, 0, 1, 0, 1. So that is a symmetric matrix. What are its eigenvectors and eigenvalues? So, let me just try to be kind of lucky about this. S of 1, 0, 1 is what? I have 1, 0, 1, 0, 1, 0, 1, 0, 1, applied to 1, 0, 1. When I compute this, I get 2, 0, 2, which is 2 times 1, 0, 1. So 1, 0, 1 is an eigenvector. With eigenvalue 2. 2 times this vector, S of this vector is 2 times the vector. So 1, 0, 1 is an eigenvector with eigenvalue 2. Let's see, we're lucky. Let's see how lucky we can be. What about what about S of 0, 1, 0? You have 1, 0, 1, 0, 1, 0, 1, 0, 1, applied to 0, 1, 0. I get 0, 1, 0. So 0, 1, 0 is an eigenvector with eigenvalue 1. That's one eigenvector. That's another eigenvector. One, 0. So this is really unfair, but let me take S of 1, 0, minus 1. 1, 0, 1, 0, 1, 0, 1, 0, 1. Apply to 1, 0, minus 1. This is 1, 0, minus 1. That's 0. This is 0. And this is 0. So, which, if you like, is 0 times the vector 1, 0, minus 1. So this is an eigenvector, 1, 0, minus 1, is an eigenvector with eigenvalue 0. That is, this is in the kernel, S of this is 0. Everything in the kernel is an eigenvector with eigenvalue 0. So and these three vectors, if you check, these are linearly independent. So this is an orthogonal set. If you want an orthonormal set, you just divide each by its length. So suppose I let, now And I want the eigenvalues, they're 2, 1, and 0. These are actually in decreasing order. I want to take the square root. So I want to take V1 to be 1 over root 2, 1, 0, 1. This now has length 1. V2 to be 0, 1, 0. That has length 1. And V3 to be 1 over root 2, 1, 0, minus 1. So now these three vectors form an orthonormal basis. This is an orthonormal basis of eigenvectors of S with eigenvalues 2, 1, and 0. 2, 1, and 0. What is my rule for constructing the W's? I want to let W1 be 1 over the square root of the eigenvalue times A of that thing. I want to let W be 1 over the square root of 2, the eigenvalue, times A of V1. What is this? This is 1 over the square root of 2. A, that's my original matrix. The original matrix is 1, 0, 1, 0, 1, 0. And V1 is 1 over root 2 times the vector 1, 0, 1. So 1 over root 2 times 1 over root 2 is a half. 1, 0, A of 1, 0, 1 is 2. Zero, which is 1, 0. 1 half is 1, 0. W2 is 1 over the square root of 1, A of V2. 1 over the square root of just 1. This is just 1, 0, 1, 0, 1, 0. What was the vector V2? The vector V2 was 0, 1, 0. So this is equal to 0, 1. Actually, E2, so it's E1. That's it. So we have the basis for R3 are the vectors W1, V1, V2, and V3. V1 equal to 1 over root 2, 1, 0, 1. V2 is 0, 1, 0. V3 is 1 over root 2, 1, 0, minus 1. My basis for R2 is W1 equals E1, 1, 0. W2 equals 0, 1. And what is the matrix for A with respect to these bases? So A of V1 W1 is defined to be root 2 A of V1. A of V1 is root 2 W1. So this 2 by 3 matrix, this will be root 2, 0. A of V2 is E2, which is W2. So this is 0, 1. A of V3, what is A of V3? The matrix A is 1, 0, 1, 0, 1, 0 times V3, which is 1, 0, minus 1 times 1 over root 2. If I do this calculation, I get 0, 0, 0, 0. So this is my matrix with respect to this new basis. I have this diagonal matrix and everything else is 0. Okay, well, if anyone is interested in going further in linear algebra, one of the things you will do is spend a lot of time understanding the singular value decompositions, the theory, the algorithm to compute them, the geometrical meaning, and how they have many, many applications in data analysis and many other areas. Okay, well, that was a lot of work, and that's it for today. I'll remind everyone that 7 o'clock tonight, I'm on Zoom for a problem session, and everyone's encouraged to show up.